All right, we are now going to begin a precipitation problem. In a precipitation, we're going to use the reaction quotient again. RxN stands for reaction. And we're going to be able to use this to compare to the KSP to determine if a precipitate, which is simply a solid, will form, or if no precipitate will form, or if they will just stay in equilibrium, meaning they'll just go back and forth, so no precipitate will happen. So if Q is greater than KSP, then a precipitate will form. If Q is less than KSP, no precipitate will form. So the formula is the same as KSP, just like equilibrium. The reaction quotient will need to be compared to K to determine what is going to happen. So here is our question. A solution of a 75 milliliter of 4 times 10 to the negative third molarity of CeNO3 is added to 300 milliliters of 2 times 10 to the negative second molarity of KiO3. Will CeIO3 make a precipitate? If so, what is the concentration of the ions? So we first need to determine if a precipitate will form. So our first job is to figure out what Q is and how it compares. Our problem lies in the fact that we are going to take two different concentrations and two different volumes, and add them together. So our reaction will be as follows at the top. We're going to have CeNO3 plus KiO3 reacting to form CiO3 plus KNO3. We need to balance our reaction first by adding 3. Since we had 3 NO3s here, we need to therefore have 3 NO3s here. We know that the charge here was also CeIO3, so there was 3 here. So therefore we had to have a 3 in front of here as well. This is an aqueous solution. This one's an aqueous solution. We are trying to determine what type of solution this is, and we know this is an aqueous solution. So the problem we're looking at more directly is CeIO3. So we're going to go ahead and break this one down. So we have CeIO3, and we're going to have the reaction as follows. Ce plus IO3, well, those are ions, and so our Q is going to therefore equal the concentrations of each of those. We know the concentration of CeNO3 and the concentration of potassium and KiO3. Those are the concentrations we know. When we add them together, we're going to get different concentrations. So what we need to do is determine the number of moles of each compound that we have. So what we're first going to do is we're going to determine the number of moles of Ce and NO3. So we're going to take the 4 times 10 to the negative third moles over 1 liter equals X, our number of moles, all over 0.75 liters, the amount we were given. So to determine this, we will times 4 times 10 to the negative third times 0.75. When we do that, we get 0.003 moles of CeNO3. Once we do this, we have to then look at the relationship between the moles of everything. So 1 mole of NO3 equals 1 mole of Ce and 3 moles of NO3. This is because if we look here and here, we have 1 of these and we have 3 of these, so therefore 1 mole and 3 moles. So we're going to take the number of moles we have here and we'll multiply it by 1 to get Ce and multiply it by 3 to get NO3. So let's go ahead and continue doing that on our next part. So we had 2 molarity, 2 times 10 to the negative 2 molarity of KiO3. So then we want to put an X on top of that, and then our number of milliliters we got over, and change it to liters. So we're going to cross multiply here, and then we're going to get our X, our number of moles. So we have 2 times 10 to the negative third times 0.3. This gives us 0.006 moles of KiO3. Once we have the number of moles of KiO3, we then compare it to how many we have each. So for every 1 mole of KiO3, we have 1 mole of K and 1 mole of KiO3. Therefore, we have 0.06 moles of KiO3, 0.06 moles of K, and 0.06 moles of IO3. Our new job now is to determine the molarity of Ce and IO3, so we can use this equation up here. So what we're going to do is we're going to take Ce, and we're going to take the number of moles we have now, and we need to put it over our new volume, because we now have 0.75 liters and 0.3 liters, and we add those together to get our new volume. This is why our molarity, or our concentration, is going to change. So we have 0.3 all over 1.5 equals 0.00286 molarity. Then we want to also determine the concentration of IO3, which is going to equal 0.006 all over 1.05. This gives us 0.00572 molarity. Once we have these two numbers, we are then welcome to plug them into the top equation. So now we're going to come up here and plug them into our top equation. We're going to multiply this by this number cubed. Again, we get this number cubed because of the number of moles here in the front. So this one is cubed, and so therefore this number needs to be cubed. When we multiply them together, we get 5.33 times 10 to the negative 10th. Then we want to know what is the relation between Q and KSP. We know that KSP, from reading our question again, is 1.9 times 10 to the negative 10th. And K was 5.3 times 10 to the negative 10th. So therefore, they're in the same powers, but this number is bigger, so therefore Q is bigger. This means that we are going to get a precipitate. Yay! Because remember, if Q is larger than KSP, a precipitate will form. Yay! So our next job is to then determine the concentrations of everything. The concentrations of K and NO3 is going to be just like we determined the concentrations of our other ones. We're going to take the number of moles we received earlier, back over here, we did our moles. So we have our moles of 0.006 all over 1.05, so our moles all over our new volume, equals our new concentration, this number right here. We're then going to do the same thing for NO3. Our number of moles of NO3, all of our new volume in liters, will give us our new molarity of KSP. However, since we now have some solid forming for CE and IO3, we have to determine its new concentration with that taken out. So those are going to leave, and we also have to determine the concentration of the ions still floating. So we're going to have to do a new equation. This we're going to do is we have to use the KSP. So we want to know if we're at KSP, what is the concentration of CE and IO3 to the third. So what we're going to do is we're going to plug in X for CE, and then since we have 3 IO3s, we're going to take a 3X raised to the third power. So when we do this, we get 27X cubed. And then we have 27X cubed times X, which gives us 27X to the fourth. This is going to equal our KSP. If we look again, our KSP equaled 1.9 times 10 to the negative 10th. To be able to solve this problem, you'll need to divide both sides by 27 and then take it to the 1/4 power. It looks something like this. You're going to take 1.9 times 10 to the negative 10th, divide by 27, and then raise it to the 1/4 power. Make sure you do have parentheses around that caret and the 1/4, which is going to give us X. We know that X was equal to the concentration of CE, so X is equal to this, which is also our concentration of CE. However, IO3 was 3 times that amount, so we have to take that amount and take 3 times the amount of X to get this amount of concentration. Once we have done that, we have solved the problem, and that is the end of it. So make sure you're practicing. This is a long problem. Try a quiz question. Try breaking it down into each individual parts and get working. Come to me with questions. Take your quizzes.